Dr. Rita Khatir to the stage. Dr. Rita Khatir is an active lecturer and researcher in Agricultural Engineering Department. She got her master's and doctoral degrees in food processing from Georg August Universität Göttingen, Germany. Ladies and gentlemen, please welcome Dr. Rita Khatir.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa ashabihi ajma'in. First of all, let's thank Allah who has given us myriad blessings, and then prayers and peace to our Prophet Muhammad sallallahu alaihi wasallam. My honorable to all professors, doctors, college presenters, and all participants of our hybrid conference today. I would like to introduce myself. My name is Rita Khatir, and I will be a moderator for our second session today. Ladies and gentlemen, actually we had invited two keynote speakers to our session. However, unfortunately, we will have only one speaker since Professor Dr. Bart Nikolai is sick. We wish that Professor Nikolai is getting well soon. Okay, then it is a pleasure for us to welcome our keynote speaker from Germany, Professor Dr. Daniel Morlein, as our keynote speaker. And Professor had joined us virtually in Zoom rooms. First of all, I would like to introduce you about Professor Morlein. Professor, can you hear us? Guten Morgen, Prof. Okay, we will check later. Professor Morlein is a professor. Guten Morgen, Prof. Okay, I will introduce you to all participants. Professor Morlein is Professor for Quality of Animal Products. He worked as professor at Department of Animal Sciences, Georg August Universität Göttingen, Germany. And you can follow also his publication on Scopus. He had published about 72 papers indexed by Scopus, with each Scopus index of 25. He has wide areas of interest, including NIRS, near-infrared reflectance spectroscopy, endogenous and exogenous factors influencing product quality, use of alternative protein sources in animal nutrition, dual-purpose chicken breeds, alternative to piglet castration without anesthetization, method for physicochemical quality assessment, quantitative modeling for quality characteristic, consumer behaviors and acceptance, sensory perception, and also about biomarker for quality assurance. And today, Professor Morlein will give the speech for us under the title Near-Infrared Reflectance Spectroscopy for Sustainable Agriculture and Food Production, Past, Present, and Future. So, Professor, are you ready? Okay, Professor, the time is yours, please.
Good morning.
Good morning, Prof.
Good morning. So, can everyone see the presentation already?
Yes, we can see
Is
clearly.
it? Excellent. Thank you, Dr. Rita, and also the organizers for inviting me. It is a pleasure to be here this morning, early morning in Germany. And let me say that it is 40 years ago that I had my first connection to Indonesia. It was in 1983 when my parents moved to Indonesia and I stayed there for 2 years. basically as a kid. We returned in 1985, and I'm very happy to have a collaboration with Dr. Agus Munawar, who did his PhD here with us in Göttingen, also under my co-supervision. And today I will, as already presented on the screen, talk about near-infrared spectroscopy and how this can contribute to sustainable agri-food systems. So thank you again for inviting me, and for those who are not familiar where I come from, I have a map here. This is Germany, so at the center of Europe, and in the center of Germany you would find Göttingen with a very beautiful old university, and maybe some of you have had the chance to travel and visit some of our nice landscapes or taste some of our foods. I will talk about near-infrared spectroscopy, and I put this under the title of sustainability, and I borrowed a chart from an esteemed colleague who is actually president of the International Council on Near-Infrared Spectroscopy, and he recently presented in Innsbruck at the biannual meeting challenges related to food production, which you also might be dealing with in your context. So there is a lot of challenges like climate change and growing population and resource overexploitation, and there is some new approaches that might help mitigating those challenges. And very often measurements are involved, which are here called foodomics, so measurements that characterize foods, be it in cellular agriculture or with processing of food itself. And at the very end, we want to achieve more resilience, more sustainable production, and also save resources. And I hope I can make clear with the presentation how NIRS can contribute to that. And I have put a quote at the very beginning of my talk by a very old and maybe known physicist who stated that only when you can measure things you can also improve it. So it all starts with measuring things, and NIRS can indeed help measuring things, and I hope we will be able to see all together. It can measure things quickly, reliably, and also in a sustainable way in itself. I hope I can make clear that during the talk. I have put together information, a little bit of information about the background. So what is NIRS, how does it work? I will highlight a bit on some stages of evolution of NIR instruments, and will highlight some examples what is possible today, so how is it used already, and at the end I will also touch on current developments and give an outlook of what might come. I'm not sure, of course, who of you is familiar with NIRS, and this is why I decided to put together some slides, some information on how NIRS work, so some fundamentals. And I would like to start with this figure which shows the electromagnetic spectrum, and I want to highlight here that NIRS had been discovered as being part of the electromagnetic spectrum, and let me see whether I can use a pointer as well. So this is the NIRS range, so from about 800 nanometers to 2500 nanometers, so just above the visible range of the electromagnetic spectrum and before the mid and far infrared. And the interesting thing, once it has been discovered, the interesting thing is that near-infrared light interacts with organic molecules. So basically organic molecules absorb energy because they vibrate. So they take up energy for different types of vibrations, which are given here in this figure. These will not be too important. Just maybe keep in mind that there is very many types of vibrations. And of course, we have quite a number of different molecules, mainly molecules linked to hydrogen, so like OH as in water, or CH like in fats, for example, or NH for proteins. And these vibrations depend apparently on the composition of a sample. And near-infrared spectroscopy makes use of exactly this interaction, so let's say of this absorption of energy. With this figure, which is only schematic, I wish to highlight that there is different principles how instruments can be built and how this absorbance is being measured. And this could be either in transmission, so that the light travels through a sample, maybe like the liquid traveled through the soil, as we have seen in the before presentation, and then it is detected. And very often, actually, reflection or reflectance is being used. So the light travels and interacts with the matter, and then it is reflected and detected by some detectors. And maybe later we will touch an application which uses interactance reflectance. This is very often used with so-called fiber optic probes, where there is one channel maybe sending the light in the sample and another channel which then later detects the sample. And with this chart, which I have borrowed just to exemplify what is known by now in terms of these interactions, it has been discovered that for the range, so for the wavelength range of near-infrared light, where these absorptions have their patterns in the spectrum. So, for example, we have a region for third and second and first overtones. So I will not go into the details of this, but you can see from the figure that there are regions which are associated with certain molecules, with certain bonds, and there also is a type of pattern which is repetitive. I will make this more clear with my next slide, which eventually shows a true spectrum. What you see here is 3 spectra. Actually, you see 6 because it were replicates. But you see 3 spectra from 3 different products. So there's a tea, there's ground black pepper, and there's some olive oil, which for sure differ in their composition. And exactly this is to be seen already from the spectra. I will just highlight a few things here. For example, that here is characteristic peaks here and also here, which are very typical for fat, so for the CH bonds. And if we go to T, for example, we will find characteristic peaks that are related to moisture, for example. And if you are interested in that, there would be textbooks, tables, where from previous research those band assignments have been done. So whenever you collect a spectrum, you find characteristic peaks. You could, for the very beginning at least, consult such a table and get the first idea of what is maybe present in the sample. It is, however, not only chemical composition that is reflected in the spectra, it can also be physical properties. And I borrowed this example which is on sucrose, so sugar. And here you see again 3 spectra, but now it is always sugar, sucrose. What is the difference? The difference is the physical state. So we have amorph or fine or coarse sugar. And you can clearly see, hopefully, that the spectra differ remarkably. And this has to do with scattering properties, which are also increasingly being studied. So this is more fundamental research in the field of NIRS to identify those sources of scatter, and particle size specifically affects the scattering properties and can make such differences as to be seen here. And if you, for example, work with coffee, it might be a difference whether you have a very fine powder or whether the powder is only coarsely ground, even though we will later see there is ways to correct for such, let's say, unwanted effects in the spectra. With this, I would like to move on and just highlight in a very simplified manner what is done, and not without respect, I would like to say that near spectrometer without chemometrics is like nothing. It's not too much of worth. What needs to be done actually is to make use of that spectral information, and this is typically done by a lot of multivariate analysis with different types of programs available for that. And then typically there will be a sort of calibration model for prediction of quantitative traits or for classification. And then you will hopefully be able to use this in a practical application. I will come back to an example of wood, which I find very impressive later on. If you want to go more into details of that, I will just touch a bit on what is being done, and very often it starts with a proper experimental design. So take decisions about what samples to include, how to arrange the measurements, and then it is about data processing. And typically one would spot for outliers, remove noise and artifacts like I've just shown briefly. And then it is about data exploration, which I feel always is a good idea to first have a look at the data and see, can you already identify patterns, peculiarities, and then start, for example, also with outlier detection. And only then you would continue with true model building, and many people have done this manually in the past, so trying all sorts of pre-processings and all sorts of modelings, and then to compare the performance of those models and to see which gives the best predictions, which are then to be validated with hopefully proper validation data sets, so independent data sets, to make sure, hopefully sure, that the model can be applied in the field, for example. And then validation is a very crucial step. And I will only highlight one aspect about this pre-processing, for example, which has been discovered, is very effective in removing like unwanted effects, and derivatives, for example, that you see here can do a lot. And you see here that there's 3 like make-up spectra which have something in common, which is like these 2 peaks. You would find them in all 3 of the spectra, and the peaks have some wave numbers associated with it. And if you start with the first derivative, which is the middle figure, you can see now it's only two lines above of each other, and the black and the blue, they have become identical because only this constant offset was removed. While we see the red one has a constant offset now with the first derivative, and this is due to this like increase, so this multiplicative effect. And this also gets reduced. Now we have only one like identical pattern after we have applied second derivatives. So this derivative thing is very effective, can be very effective in removing unwanted artifacts. It can, however, also occur with additional noise. So with this, I only want to have highlighted and outlined the principles. There is probably hours of talk that you can spend with explaining all types of modelings. I don't want to do that. I rather want to show some applications. And let me start why actually NIRS has been studied so frequently. And this is because traditional laboratory methods, as you might be familiar with, very often are slow. They involve a lot of labor and maybe also chemicals, instruments that are costly. Sometimes they can even be unreliable or difficult. And very often you have to bring samples to a lab. Not to speak of that for many targets, so for many measures, you would have to do a separate analysis. And the advantage of NIRS comes into play as we will see that it is quite fast. So to acquire a spectrum is within a minute or even less. It can be seconds also. It is very cheap once you have the instruments. It is typically also reliable, easy to train, and we will later see you can also bring instruments into the field. And by this you can analyze a lot of samples. And this was some very brief and fundamental introduction, and I would like to move on and show some examples, and I would like to start with, let's say, the foundation of widespread NIRS application, even though at that time sustainability was not yet such a big theme as it was today. And there is one person who is acknowledged, widely acknowledged in the field as the inventor, let's say, or the father of near-infrared spectroscopy. It is this person here. This is Carl Norris, an engineer who worked with the USDA, and he originally invented a machine to sort eggs. So this is a candling of eggs, and this was so impressive at those days that the former president of the US, Eisenhower, went to see this machine. And later on, and this was in the 1970s, Carl Norris then developed, let's say, the first spectrometer to be used for predictions, really. And I have not met him in person. I have only recently spoke to a professor from South Africa who actually worked with him, and Phil Williams, who put together a nice report. But what is known is that, let's say overnight, in Canada, for the Canadian Grain Commission, where they tested like over 600,000 samples of wheat per year for protein, they kind of overnight replaced the chemical determination with NIRS. And this alone served like 50 tons of sulfuric acid, which is needed to measure protein, could be replaced. And not to speak of the advantages of speed and also costs that came into effect when they introduced NIRS. And from that on, of course, it took some years, like often innovations take some time. This is called the green analytical revolution, and you will later see what the big advantage of NIRS can be. So that was in the 1970s, around 1975, when I was born, actually. And since then, a wide range of instruments have been developed, and maybe you were already in touch with some of them. So there is a lot of benchtop devices. So I took this slide from a colleague from Belgium who have like 25 years of experience with NIRS. They have a lot of these instruments. And meanwhile, you see already there's smaller instruments which here are called baby NIR. And I will later touch a bit also on near-infrared imaging devices, which add some complexity, but which also add some new opportunities for near-infrared spectroscopy. So when you start working with NIRS, there's one good thing: you would find plenty of literature, not only original papers, but also reviews. And here I have put together a slide just with a number of review articles which cover the subjects of NIR and food. And I just selected review articles, and you find plenty of them, which might give already some indication this is widely used in the field. And why is that? Because near-infrared has a major advantage: it is non-destructive, and it can predict many traits at the same time, more or less, at least when you have calibrated for it. So with this cartoon, which is from a Danish colleague, I think it's already clear what is meant. That typically, if you want to have a chemical analysis, you need to take several samples, and at the end, your product is gone, and you have to do the analysis one by one. Whereas with spectroscopy, it is sort of remote. Of course, sometimes you have to touch the instrument, or the product has to be put to the instrument, but it uses no chemicals. And as I said, you can do a lot of predictions at the very same time. And it would not be possible actually to list them all. I have only a very brief list, which should only give an indication of this can be things like proximate composition. So apparently, organic matter is very rather easy to predict. So protein, fat, and moisture. But this could go to quality traits like acidity in fruits, sugar in fruits. It can be gross energy, fat and protein, dry matter in cheese, hot. But it can also be texture attributes, and lately also volatile compounds. And let me say that I would not be able to say there is a general rule of what is possible and what is not, but typically a lot is possible with NIRS, and very much depends on how to set up the experiments to establish a calibration. And maybe also, I just want to highlight, very often you would find a measure of merit, which is RPD, residual predictive deviation, and this is very often cited. If it's above 3, then this is a rather okay or a good calibration model. But I just want to highlight there is peculiarities with that, so not always only look at that measure, but sometimes it might even be okay not to have a very precise prediction, but to do a good class modeling. I will show some highlights, and to begin with, I have picked one which I found very impressive, because it also highlights how NIRS can save, as with the wheat and protein determination, can save a lot of time and also have some economic return, which very often is relevant, of course. And I borrowed this example from an Australian colleague, Roger Mader, who also is editor of the renowned NIRS journal. And he worked a lot with woods, which I found interesting for the context. APY are relevant, and the traditional method, as you see here in these photos, requires samplings of like 5 kilograms, and the labs at those days were able to analyze 6 samples a day, and it was very, very costly. And there's a happy end, let's say, about this. And this Roger Mader and his team, they developed calibrations, and you see more or less a workflow, what is possible nowadays. So now they have a very small hole, they drill a sample, which is then freeze-dried, and you see here a benchtop FT-NIRS instrument, and they were able to establish a calibration model, which you see, if you are familiar with that, is very linear, and the R-square is quite high. Prediction errors are good, and this is then being used for breeding, which is the below figure. And here you see a distribution of KPY, so of the economic trait, which by selection of the best trees, let's say, can be shifted, and you see an increase here by like 1 or 2%, and this at the first you might ask, well, is that relevant? Actually, that was quite relevant for the industry there in Australia, because that was worth more or less like $2 billion US dollars per year, based on the number of trees and so the overall tons of wood being processed. So let's say all the work put into establishing a calibration with NIRS at the very end turned out to be also economically very effective, and it of course can speed up the whole process of breeding in this case. And the same would be true for many other applications on quantitative traits. I would like to move on to another line of application. A lot, so that's why I decided to put in this example, and I put this also in the presentation because Alyssa Drees, who I borrowed the data from, it's a colleague from Hamburg in Germany, won the third best poster award at the NIRS conference this year. And I was very impressed about how straightforward she did all the analysis, and that's why I want to show it to you also. So it is about fraudulent mixtures of nutmeg, which are like adulterated with shell. And what she did was basically to have mixtures of nutmegs and shell in different concentrations. And they used a very simple reflection mode on a benchtop device. And as you can already see from this calibration figure, it turned out to be very effective. But I would like to show how it works, and would like to do that step by step. And if you remember from the very beginning that we have spectra here in blue, this is the shells. In yellow, this is the nutmegs, you can already see with the bare eyes there is some spectral differences. So it appears also from PCA analysis, which is used here to visualize some sort of clustering. You have a very clear clustering of the shells versus the nutmeg samples. And they continued with preparing mixtures, there were like 230 samples, so different mixtures of different like nutmeg samples with different shell samples, and a lot of combinations, especially in the range of 0 to 10%, because otherwise it would be too apparent also for the bare eye, like you see here. If it's only shell, then it's very, very dark. And if we move on to the spectra, again we can see there is something going on here. So we see clearly there is this blue line, which is the shell-only samples, and then there is like a gradient with increasing amount of shell in the mixture. There is a different spectral pattern, which is again to be seen from PCA. Like we have a clear clustering groups, and here of course there is some overlap, so no clear separation. I have to say though that PCA is an unsupervised classification, and there is better ways to have a classification. They moved on in their experiments with machine learning methods, so support vector machines in this case, and I would like now show you the final model. So the predictions, which actually were very good, I would like to say. So an R-square of 0.94 with an average prediction error of 0.75. And so they determined limit of detection. So that is the concentration when they were able to say, well, we do have shell in the mixture. And the limit of quantification, this is very much or very similar to HPLC or GC, where you would provide a number of limit of detection and quantification. And what I found interesting also to show here is this sort of graph, which shows the validity of the predictions by showing like in classes of below 0.5 up to 10% of shell in the mixture. And at the right-hand side of the graph, you would see the bin of predicted shell content. And if all goes into the same bin, then this would be like 100% perfect prediction. And you see it's not 100%, but it's very rare that, let's for example stick here, that this goes into a dark blue bin. So to put it into a nutshell, this fits perfectly here. The prediction is very well, and only rarely predictions are not valuable. Interesting here to say is that the reference analysis, which is a wet chemistry method, is only able to say there is shells in when the shell content is above 5%. So again, this is a very impressive example, I would say, in a relevant context, because spices are very expensive, at least here, are very expensive here. So frequently there is adulterations, for example, with nutmegs. There was even coffee powder mixed into it, because coffee was much cheaper than nutmegs. Okay, I would like to finish with that example and continue with some application which is even more relevant when it comes to industry processes. And the next few minutes I would like to spend with so-called process analytical technology, also abbreviated as PAT, P-A-T, for which NIRS has enormous potential to be used. And why should we talk about PAT? Again, this is borrowed from a colleague who's a renowned expert in the field of PET, Søren Engelsen from Denmark, and they work a lot on PET applications. And it can range from studying the raw materials to improve like the raw materials, but also to improve the later processing stage, understand what is being done. It can be in the process itself to analyze intermediate steps, for example, to improve the later product quality, so to manage product quality and not only to control the final product, but to really in the middle of the process understand what's happening. And of course, there's aspects related to environmental footprints, to maybe use less resources, less energy, less water, less raw materials to prevent waste and also to increase capacity. And I think it already is clear by now that this is very much related to sustainability of food production. And there is one further scheme that I would like to share, and this is a scheme how this can be done. There is basically two ways, and one is a so-called feed forward. So when measuring the variability of raw materials, you could then decide what to do with that raw materials in order to get a lower variability in the output product. So you can measure at the beginning, so to say, and then feed forward information to control parameters in the processing, or you can measure the final product and then see, well, is this how it was expected to be, or is it different? And then in the sort of feedback cycle, again, modify parameters in the process to guide the output. So there's two different approaches, and with like inline monitoring, which is feasible with spectroscopy, as you will see in a minute, and also data analysis, it is possible now also in real time to monitor and control processes. And NIRS has been shown to be the most often used for PET because it's non-destructive, because it's rapid, also because of some other advantages, which I show in a minute. So compared to other spectroscopy techniques like Raman or mid-infrared, NIR is by far often the most used technology, because it has some other advantages also, which I did not touch so far. There is, of course, far more sensitive methods like LC-MS, GC-MS, which can be very sensitive also in like the PPB range, where near-infrared is most certainly not useful, but it is very time-consuming. So a GC or LC-MS run can easily be an hour, whereas at the right-hand side of this overview figure, the spectroscopy techniques are shown, and they are much faster. And given the penetration depth of near-infrared, also there is a good mass overview of a sample. It can handle solid state products, which you cannot introduce into a LC. And there's few other aspects which really favor NIRS and why it is used. And I would like to show two examples how this has been done. And this is an example from like at-line analysis of cheese, recently published, also a Danish study, if I will remember correctly. So they have machines where the rennet or the batches for cheese making are inserted, and they travel through this cylinders, let's say, and then there will be discs cut out, and these later go into the cheese making. This is what you see here in the scheme. And they now took samples here at this control point and monitored. You see, this is from a single day only, but over time, so within the day, they could identify changes in the product properties which would not have been discovered by single samplings. So, like let's say here, important to remember is just that if you have a cheap and fast measurement technology, you can increase the sampling for at-line analysis, or, which I will show in a second, you can even integrate the measurement in the process. And the second example is also related to dairy production, also again from Denmark. Here I just want to highlight what is done. I just talked about cheese and cheese making. So this uses like 15% of the raw milk, and then there is whey, which contains a lot of, not a lot, it contains actually a lot of water, but there is some dry matter still remaining, and this is going to be used, to be further used. So they wanted to make use of the side stream in this dairy production, and retract the proteins, so lactalbumin and lactoglobulin from that milk. So this is from that 6.5, this is 10%, so a very small amount, but if you have a lot of this and if you can retain those proteins, this makes use. And what they did is basically, this is a schematic flow only. There is a process, and this like tube should only illustrate they can insert a fiber optic probe into that tube, so you can continuously monitor what is going on in the tube by recording spectra. And I will jump over all the pre-processings and only highlight what is doable with this inline process monitoring. So instead of frequently picking samples and taking them to the lab, this is shown here, they get the full overview of what is going on over time. And you can see from the green line, which is like the real-time analysis result, you would find, well, this is, of course, on average, corresponding to the dots, but there is more information in it. So the better you can integrate such probes into a process, the more you can understand what is going on inside your machineries. And I have one last example, which only is a schematic illustration, which I also found interesting enough to show it here, which is from a biodiesel research. So in this case, they wanted to make use of waste cooking oil and to further make use of enzymes to finally come up with biodiesel. So this is called third generation biodiesel. And here we have a reaction vessel with a NIR probe in it, where you can monitor the degree of changes in the fatty acid composition during the transformation into the biodiesel. And this is, of course, only a schematic aspect. You can see the prediction of the yield. So very relevant to understand in real time how process parameters affect economic traits like yield in this case. And with this, I already want to conclude on this PET technology. Again, this is a figure from Søren Engelsen, which nicely shows what is possible. So maybe here there is a black box thing. If you don't measure anything, you wouldn't know what is going on inside and just wonder, well, things are getting out of control for some reason. And maybe one step in the better direction is to insert some sensors, which then give information of what is going on in the reaction vessel. And if then finally, this is illustrated by these loops here, if you implement some control measures like a feedback or feed-forward type of control, then the process is not only monitored, but it is also controlled. And especially those time dynamics can be captured by NIRS, such as rapid responses get possible. And as I said, this might at the end save resources and also avoid waste when you have to discard products which don't have the needed properties. I have one further advancement on this. At the very beginning, I have mentioned a word which is imaging, and I would briefly also give an introduction of what is possible and what is being researched in terms of imaging, which is, I would say, not so novel anymore. I think there's cameras available for quite some years already, and they are being used for aerial inspections, so like from airplanes. But how they are used in the field of food science, I will briefly cover. And, how this is done is illustrated in this hopefully understandable figure. So there is a sort of camera which is capable of capturing more than 20. I know some cameras which can do like 240 different channels. So let's say infrared wavelengths. A sample is being put on a sample stage, which often is movable, like a conveyor belt or an XY stage. So there's a movable plate, there's a sample here, maybe you see there's an apple or something, and there's illumination needed. In here, and then spectra are recorded. As you may assume, there is now far more complex information. Let me try to explain how this looks like. We have this XY stage, so this is like the apple from above, you could say. See here. So for each pixel of the camera, we get the spectrum. So this is now like a 3D, a so-called hyperspectral cube. And there's a lot which can be extracted from such information. This overview from my Belgian colleagues just highlight where this is used. It is used in breeding, so to analyze individual grains. It can be used in archaeology to analyze the composition of bones, for example, from old materials. It can be in criminal inspection. It can be plant breeding and monitoring what's going on in the field. And also some food fraud detections. And I have picked two examples. One example is to identify impurities in powders, and this can be like flour, this can be milk powder, this can be compound feeds to spot unwanted targets, and near imaging is able to highlight now where you find adulterations, like in this case ergot powder, which is not healthy in wheat. So by putting a sample like here, transforming the data and applying some calibration models, you could identify maybe here from the naked eye. Here is the model says this is an impurity and this corresponds to these dark spots. And this is here in this example with 5% of adulteration, which I find very impressive. And I can't go into each and every detail of this study, but the spatial distribution and the spatial information of, in this case, is actually used, whereas in the classical near-infrared spectroscopy, the spatial information is more or less put all together in an average spectrum. And here the individual pixel information is used. And only to highlight what is possible with this, I would like to show the next example, which maybe you can identify already from the shape. This is corn or maize samples, which have been analyzed with a near imaging system. And as with all the other data, you can do PCA sort of analysis. And in this case, this is a so-called score plot, which has then be used to do some sort of clustering. And if now the score information is being used to reproduce some color-coded images, this is so the score directions. So let's say higher values of the PC5 get blue values and lower values get red. Then you can see those kernels differ in this trait. And if you then study the underlying loading plots, you would be able to identify which spectral information contributes to that clustering. And this can be used in many, many ways. I have one industry application from Belgium, where they studied different varieties of wheat, especially durum and common wheat, which are being used for production of pasta. And here you see the setup. So this is a moving conveyor belt. So the samples are placed here, and then they move through. And here we have a camera system. We have the light sources, as we have seen earlier in the image. And then, of course, there's a lot of mathematics behind. They can make predictions. And this is a study which uses different batches of wheat. And here we have the lines where they were introducing different batches. So this is the vertical lines. And here we have the durum wheat, durum, and then we have common wheat, durum, durum, common wheat, common wheat. And this is the percentage of pixels predicted as durum, 100%, 0%. So I hope it is understandable that by using this spatial information, throughput analysis, inline integration of NIRS is possible. And this is, of course, relevant when it comes to raw material validation, in-process control, monitoring and feedbacking to steer processes. And with this, I would like to come to more or less the end. I have a few more words on an outlook, and I have already mentioned some key trends, I would say, what is happening in the NIRS world. And with these photographs, I only want to highlight current developments. So there is now handheld spectrometers, which are the size of more or less my hand, which can be used with smartphones. And you can easily imagine, I think, you can bring those easily to the field. And here you see an example of how this is being used. So this is one instrument, one of very many instruments that are now miniaturized and also low cost. So let's say at least low cost compared to typical benchtop devices. So this is one of the typical prices for benchtop, and these are like 5,000. I would say this is more or less also the same in dollars. So rather affordable, and the most important thing, you can bring the instrument now to the sample instead of the other way around. So you can go in the field and measure samples there. This is one ongoing development, and I noticed, especially from one company, there is few more who do the same. That they create business models around software and calibration. So especially here for one company, if you go to visit their webpage, you will find they are not only selling instruments, they are also providing a platform for exchanging calibrations. And you would find literally hundreds of models for all sorts of applications. They have different software apps. So this is more or less like the Apple Store, I would say, for applications. So if you develop a calibration model, you can put it on their website, let's say on the portal, and then others can buy and pay you. I find this very interesting because this may help spread the technology. And there's also cloud-based computing associated with that. So you record the spectra, they are transferred to a cloud sort of calibration model, and then you see the results in real time on your smartphone. There is a third aspect, which is to be concluded from the miniaturization, and this is from a Spanish colleague. You can see here another sort of portable instrument. Here all the battery is included, and you can bring that to the field and measure, like produce. So this is vegetables and fruits to monitor and make decisions on the optimal decisions on harvesting, for example. And the very same devices, again, this is this small, like, it's more or less like a pen, a little bigger than a pen maybe. And here it is an example also from the Spanish colleagues who showed that the validation of hams, which are very popular in Spain, and where they have a lot of categories of different quality classes, so to say, where they can measure through the pack and predict important traits which are related to the fatty acid composition, from which you can trace back the feeding system, more or less. So with these handheld devices, there is a lot of new possibilities. There is, in combination with robotics, one example, I mean, you can't see the robot, but you can assume here is a movable arm. So this can automatically move and then measure at different stages or at different positions in cheese making. So in this showcase, they have developed a robot which guides the NIRS probe to measure at different spots. So then the development of the cheeses over time can be monitored. In this case, it was about the salt content. And the last thing I would like to touch is the combination of sensors. And here there is an example from Australia. Maybe you remember the wood industry there. And they put together what they call a disc bot. So they put their wood discs in here, and then with different sensors, including NIRS, but also Raman, X-ray, they comprehensively characterize the sample. So sensor fusion, if you wish, is one of the ongoing trends also to make use of, let's say, other advantages of other technologies which are not inherent to NIRS. And with this, I would like to come to an end, and I hope I was able to show and highlight what NIRS is capable of, and how it can be used, like for non-destructive testing, that you can bring it to industrial environments, to predict quality traits, to monitor processes, and what I find also very relevant in the ongoing discussions, it is not making use of any chemistry except for when you establish a calibration, but later on then no chemicals are used. So with this, I would like to close, and I would like to thank you very much for being here with me and for your time this morning. So now the sun has come out finally here in Germany. Thank you.
Okay, thank you very much, Professor Morlein, for your deep speech about NIRS. I think all participants can get the idea and can get the new information about the development in this technology. I'm sorry for the committee because I cannot interrupt the professor's speech because he just come to the end of the speech, and it is the most important information for us. For example, I had found some questions from participants, and actually when they see to the last slide, they can get the answer directly. But I want to ask to the committee, do we have the time for discussion right now or not? If we have the time for discussion, we have about 3 or 4 questions from the chat, the room chat, and maybe also from the rooms. How is it? Should we continue with 10-minute discussion? Is it okay? Okay, if it is okay, we will have some question, yeah? And we will start with the question from the room, I think. One question. Okay, sir, please mention your names and also maybe from institution. Yeah.
I learned from Professor Sumio Kawano from Japan. So thank you for your brief explanation about NIR. Actually, I have 3 questions, if it's possible. First is about the last explanation about the possible use of integration of NIR with smartphone. So actually, this is very interesting. So what I want to use, I want to ask is about how you the idea of the sensor of the NIR in the smartphone. It is mounted or attached or inside the smartphone. Which one is better? Because actually this smartphone with NIR sensor is very important for support our traceability system, especially to track from farm to table about the quality change of our food. And then the second one is about you mentioned also yes, from the loading plots we can understand which one is the most important wavelength that's related to the result of our calculation, both quantification or some classification. But still, when we present our result, some questions come out about the behind of our model. So actually the advance of chemometrics can solve any problems in NIR spectrum, for example. But the most important thing maybe what is the reason why such kind of model happen, and what is the inside what is the relation between the spectrum and the content or the chemical content inside the food. sometimes we can call as a black box, but maybe we need some another approach to solve this problem. And the last one about our experience of how we use the integrating spare to solve the problem of the very low quantity of chemical compound inside the food. For example, for coffee, the roasting process decreasing very much the content of CGA, the chloric acid. Then we use integrating spare to approach such kind of very low quantity of compound. But still, we have no very good result. So, any suggestion from you, Professor Morlein, about how we can concern about what kind of maybe approach we have to consider about how to deal with such kind of very low compounds when we deal with NIRS spectroscopy technology. Thank you for the opportunity for the question.
Okay, thank you for your question, sir. Okay, Professor, you can answer directly, I think, some point.
Thank you
Do you get the point?
I get the points. Thank you for the question. I hope I will be able to answer. Let me start with the question related to the smartphone application. I am not aware there is smartphones with NIRS sensors integrated, but what I've highlighted is more there is spectrometers which can be connected to a smartphone, so they are not. It's not integrated into the smartphone, but there is a separate spectrometer which is via Bluetooth, for example, or wireless LAN connected to the smartphone. Then all the calculations are typically, those instruments that I know at least, the calculations are done in clouds. Of course, there's other instruments where you can install a software on a tablet computer, and then you can also run calibrations on the tablet. But the spectrometer itself, like here or like this one, they typically have no built-in software for data analysis. And I'm not able to say whether at someday it will be possible to fully integrate the spectrometer in the smartphone itself. What I've heard from manufacturers at the conference is that, I mean, they need some space to put the things there. Also, there's aspects of heat, so when the instrument is being used and the temperature changes, so they need heat compensation. I'm not too optimistic this will one day fit into a smartphone. For the second question regarding the loading plots, I'm not 100% sure whether I understood the question correctly. Whenever I was at the conferences and talking to people, and also let's say the editor of this NIRS journal, Roger Mather, he always mentioned, well, you should show the loading plots to make sure it is truly spectral information that is relevant for the calibration model, and then the other important voice in those discussions is there should also be a thorough understanding of what is going on in the sample. So there should be some chemical knowledge, and very early in the presentation this morning, I showed the table with which molecular formation has which absorbance at what spectral range. So there should be a link between the chemistry and a bit of the physics and the spectral information. I'm not sure whether this answered your question sufficiently. And for the last one, you mentioned the coffee analysis for chlorogenic acid, which, to be honest, I'm not familiar whether this is still in the ppm or even lower range. If you get into the very low, let's say, range below 0.1%, it might really be difficult to make use of NIRS. So this is a limitation. So if it comes to very low concentrations, this might be just too difficult for NIRS, unless there is correlations to other compounds or to the physical state. And just to give one example, typically you would say ash, so minerals, cannot be measured with NIRS because they don't have a absorbance in the infrared. However, there is applications to predict ash because it is correlated to, for example, shifts in the water bands. This is what I have learned at least. So there's indirect effects. And for the specific case of the chlorogenic acid, it might be the case that this is simply too low of a concentration, so it could be measured with NIRS.
Okay, thank you, Professor. I think you had answered the question. And now we have two questions from the room chat. The first one is from Dr. Agus Arif Munawar about, are there any specific safety concerns associated with using NIRS for real-time quality assessment in food industries? And the second one from Ms. Rohani Hasbullah, it is asking you about the price. Yeah? What is the price for NIRS spectroscopy? And then if we have NIRS spectroscopy, we should also have a laboratory for traditional analysis for calibration purposes. So then the second question from her is, every sample to be measured needs calibration data. Can data calibration be applied to each different sample, such as fruit grain, eggs, cheese, etc.? Thank you, Prof. I think this is the last question from us.
Okay, thank you. I will start with the question regarding safety concerns. And I'm not aware there is a safety concern when integrating NIRS sensors into a process stream. It has been applied already, and so typically it is there is either contact or non-contact. So sometimes they put a window into a quartz window into a tube, for example, and then the sensor is attached to that quartz window, and this quartz window can be cleaned as like the stainless steel tube will be cleaned in the process cleaning. So I would say the short answer is no. There is no safety concern when applying NIRS to real-time assessments. The second question was related to the price of the instruments, and as I have tried to highlight, it is a very big range of prices, and these latest and the cheapest instruments that I've seen, they are about €1,500. So let's say $1,500 US. So this is the cheapest that I have heard of, and then it goes up to like $3,000 and $5,000 for the portable ones. There is a more advanced, which is also widely being used. This is about $15,000, and the most sophisticated benchtop devices, they can cost up to, I don't know, $80,000-$90,000, and there is something in between, of course. But I don't have the full overview, but this is the price range, I would say, is typical, even though this might be entirely different when you have a manufacturer selling the products in Indonesia, for example. So this is for the prices, and the last one was about calibrations, and there is different approaches. Most often, you would have to establish a calibration for the specific type of product that you want to study. So if you want to study apples, you would do sugar content in apples and maybe also the hardness of apples, etc. And with this calibration, you might not be successful in measuring, I don't know, cucumbers. So when you then want to measure cucumbers, you would need to establish a set of parameters for cucumbers. There is one exception. When I think about feed, animal feed, for example, there is something which is called global calibration. So maybe there is a calibration which is measuring the protein content in grain samples. And grain now means wheat and rye and barley, for example. So it all depends on a very critical inspection of the models, and it can be the case that you can have one calibration like for fat content in meat, which is universally good enough for chicken meat and also for beef meat at the same time. But I'm not able to say that this is always the case. So the most often you would have like to develop different applications. But nowadays, when you buy an instrument, they can provide already a large range of calibrations for different kinds of products, from my experience at least.
Okay, thank you very much, Professor Daniel Morlein. And as moderator, I will also close our session, and I have took some conclusion also from this speech from our professor, that it is very important for us as a scientist or researcher to think about a good measurement, because to measure is to know. If you cannot measure, then you cannot improve, as Lord Kelvin said. And then NIRS also offers us a green analytical revolution, and it is very important for sustainable agriculture. And there is also a possibility to bring inline analysis rather than offline analysis. So we learn from corona virus that we have offline. We can do online meeting, online seminar rather than offline seminar, and then now we can do hybrid conference or seminar, for example, after we learn from corona. And also from NIRS, we have something new, that is inline analysis. Okay, last but not least, danke for Professor für Freundlichkeit und Verständnis für deine weisen Worte, die Wissenschaft von Leben, das Ziel des Wissens. Thanks, Professor, for kindness and understanding, for your wise word, the science of life, the goal of knowledge. Professor, thank you very much. You have delivered us a speech containing great ideas. Hopefully, it will provide strong motivation for all participants. And for all participants, especially our students, it is said in German words, manchmal muss man erst das falsche Weg gehen, den richtigen zu finden. Means that sometimes we should firstly run on wrong way, before then we can find the correct way. So good luck for us. Don't forget to work hard with love to result a great work. And Professor, please don't leave the room Zoom because the committee will deliver you some things, but I don't know what is it. And I will close this again. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.